What if the coding leaderboard was measuring who could pass the test, not who could survive a real engineering task? This is fluid coding and AI, and DeepSWE is Datacurve's new benchmark built around that exact problem. It is not just asking which frontier model writes code. It is asking which coding agent can stay useful across a messy, multi-file engineering task. The practical question is simple. Should developers trust the new spread in these scores or treat DeepSWE as one more benchmark that will eventually get optimized away? By the end, the useful answer is not just who ranks first. It is what this benchmark tests, where its evidence is strongest, where the caveats are serious, and how much weight you should put on it when choosing a coding agent. DeepSWE is a Datacurve benchmark for frontier coding agents on original, long-horizon software engineering tasks. The public corpus has 113 tasks across 91 active open-source repositories. The language mix is mostly TypeScript, Go, and Python, with smaller JavaScript and Rust slices. Datacurve says the tasks were written from scratch instead of adapted from existing public pull requests or commits, which is central to the contamination argument. The critique behind DeepSWE is that public coding benchmarks can start to saturate. Some tasks become familiar. Some fixes are traceable through public history. Some tests reward matching an expected implementation instead of matching the external behavior users actually need. When that happens, a leaderboard can make frontier systems look closer than they feel in real development, or it can reward benchmark-aware behavior that would not help inside your codebase. The benchmark uses Harbor-style task folders, metadata, an instruction, an environment, tests, and a held-out reference solution. The important detail is grading. Datacurve says DeepSWE uses program-based behavioral verifiers. The verifier should accept any externally correct implementation, even if the agent uses different internal names or a different structure. That is the design goal: less reward for memorizing a patch, and more reward for building the behavior the task asked for. The first-party leaderboard puts GPT 5.5 at about 70% pass at 1. Then there is a clear drop. GPT 5.4 is around 55.5%, and Claude Opus 4.7 is around 54.2%. After that, the public table falls sharply through Claude Sonnet, Gemini Flash, smaller GPT, Kimi, Mimo, GLM, DeepSeek, Qwen, Haiku, and Minimax Rose. The spread is the story. Datacurve is arguing that this suite separates frontier agents more than saturated benchmarks do. DeepSWE is not just hard because the prompts are long. In Datacurve's corpus statistics, DeepSWE prompts average about 2,158 characters. SWE Bench Pro prompts average more than twice that. But the reference patches tell a different story. DeepSWE averages about 668 lines across 7.4 files. SWE Bench Pro averages about 120 lines across 5.1 files. So the stress test is less about reading a giant prompt and more about making a larger coordinated change. The examples make the point concrete. One task asks Happy DOM to abort pending body reads cleanly during shutdown. Another asks Prometheus to fix label sorting across typed and untyped values. Others add config file parsing to Cliffy commands, deterministic conflict detection to YJ's maps, trap core dump generation to WASME, or XML diff, patch, and merge operations to etree. These are not tiny syntax puzzles. They look like repository work: understand the project, touch the right files, preserve existing behavior, and prove the new behavior. DeepSWE's strongest technical claim is about verifiers. Datacurve's critique artifact reports a reviewed DeepSWE sample with a 1.36% total bad rate, compared with 32.45% for SWE Bench Pro in the same critique framing. The report also describes SWE Bench Pro false positives where agents inspected benchmark artifacts such as Git history to recover gold fixes, and false negatives where tests were too tied to private helper names, missing fixtures, or unrelated failures. That evidence is useful, but it is not perfect. The audit used LLM-assisted critique, so treat the exact percentages as first-party data. There is also a behavior signal. Datacurve's verification behavior artifact says stronger models wrote more new tests on DeepSWE than on SWE. Bench Pro. For example, GPT-5.4 authored new tests in 462 of 542 classified DeepSWE trials versus 16 of 90 classified SWE Bench Pro trials. Claude Opus 4.7 shows a similar pattern. That does not prove the benchmark is perfect. It does suggest the tasks push agents toward a more normal engineering loop. Inspect. The caveats are big enough to change how you should read the leaderboard. First, this is first-party work from Datacurve, and no independent replication was found in the research base. Second, every official score used Pier running mini-swe-agent on Modal. That shared harness improves comparability, but it may hide strengths from native tools like Codex CLI, Claude Code, Cursor, or Gemini CLI. The corpus also focuses on active open-source repositories with at least 500 GitHub stars, covers 5 languages, and underrepresents bug localization and refactoring. And because my practical read is this: DeepSWE is useful because it moves the conversation from "can the model produce a patch" to "can the agent sustain engineering behavior across a repository?" Use the leaderboard as a pressure test, not as a universal ranking of every coding product. The best evidence is the task design, the public trial visibility, the larger multi-file patch profile, and the verifier critique. The weakest parts are the first-party scoring, the single harness, the limited language mix, and the normal decay that comes when a public benchmark becomes training data. The important takeaway is that long-horizon coding agents need long-horizon evaluations, and those evaluations need scrutiny too. If this helped you separate the benchmark signal from the benchmark hype, like the video and subscribe to Fluid Coding and AI for more practical coverage of AI coding systems.